So weird.
All right, we should be recording now.
Yeah, so I can't remember anything. I remember school. I was I know we were going to be that. But I at least had some one thing is I remember I was so much more. And there was like
All right, did we do this slide? Did we?
We are, right?
That's where we are, right? Okay, okay. That's what I was thinking. I was thinking, I ran out of time.
I don't know. Let me look at my friend's colors.
Okay, it's like freezing in the office and it's really hot up here.
But the advantage
It's really hot up here. It's like we can't win. I guess somebody thinks all my writing. Okay, so it says predict the major product. Okay, so what do you think you're going to get when you take an alkene plus ethanol and sulfuric acid? So what do you think the sulfuric acid is? It's going to do to the double bind. Okay, and add a what? What gets added? What? A what? An H. Yeah, just an H. It wasn't a trick question. Okay, and then what do you form after you add that H? What happens to the organic molecule? What do you get? So, okay, here's our acid. Okay, so this is going to grab a H, and that's going to go there, and what do you get? A what? Which carbon gets the H? The left one or the right one? Right, because that makes this one what kind of carbocation? Tertiary. So you're going to make a more stable carbocation. Okay, then what happens? We got that far. It was hard, but we got there. All right, now what happens? What else is in there? What else we got? Hint, it's on the slide. What? Ethanol. Yeah, okay. So what is ethanol going to do? The O, the lone pairs on the O are going to go to the what? Yes. Okay. And then what happens? You have to deprotonate the O. All right. So what do you get? Now, can you draw the product? Take a stab. Because you know you're going to have to draw them on the test, right? By the way, do y'all know, did I tell you about assessment testing? Okay. Assessment testing, normally they cancel classes. This is the first semester. They are not doing that. If you get called in for assessment testing and get this fancy letter, you get an excused absence class. We actually have a test scheduled on that day. So we will have a test that day and we'll have a review in the morning, just like regular. Okay, so I didn't realize I had done that until later, and then I went, oh, now do I move all this? What do I gotta do? So anyway, fine. So we've asked them to do that for like 10 years since they started doing it. It's fun for us. Like, oh my gosh. What? You're going to take the assessment. You're going to go offer to take the assessment test because that's better than taking the organic 2 test. Okay, is that what you wrote? Is that what you wrote? Okay, good. All right, now, when it says H3O+, okay, what does that mean? Because you'll see it like that in the book and stuff, and on other exams and things. They won't necessarily write H2O and H2SO4. You can write it that way, or they'll just write H3O+, which is called hydrogen. Okay, so what are we going to make from this one? We're going to protonate the double bond and form a carbocation, and then what adds? Water, and then it gets deprotonated. Those are like the steps in the mechanism, okay? So what do you get over here? What is the product? What kind of compound? What? You're all being scared? What's the deal? Yeah, it's just that, right? Make an alcohol. Okay? All right, I hope that's enough review. I opened it, didn't I? Okay. So somebody work me that. Yeah, here's one. Oh, he should sit there, doesn't he? I don't know if I should tell you this, but one time we were in class and Jeremy wasn't there. Jackie and I went to lunch after class. He was there. Yeah, I made a point to say hi to him. Okay, let's review again, shall we? Okay, so since there was such a mix of answers. All right, so what happens first? What are we gonna do? We're gonna do what to the double bond? We're gonna what? Protonate it, right? Okay, so that means we're gonna take one of these H's and the electrons go to the O. All right, so what do we have at this point? Oh, the thing is like off. All right, so who gets the H, the left carbon or the right one? The right one, because what do we make? A carbocation. Okay, you're looking at primary versus secondary. Okay, now what do you think happened? What? The answer is C, I got it wrong. Okay, here's a clue. What do you think happens?
I don't know. I got it wrong.
This is what kind of carbocation? What's the most stable? Can we make it tertiary? Yeah, you got to remember to look for that. So our hydrogen is going to go over there with a lovely little hydride shift. See, I'm like, oh. So now we have a tertiary carbocation. Now what adds? Water, and then we deprotonate. So which one is it? E. Okay. Are you back with me? Anytime you make a carbocation in a mechanism, you can have rearrangement. So you got to look for it like every time. Just be mistakes. Okay? So don't forget to look for those. Golly. Friday of the first week. Okay. Now, what if you wanted to make that other answer on this question? What if this was the one you really wanted to see? Okay? You're going to have to come up with another way to get it. And somebody did that. Isn't that nice of them? Because somebody already figured it out. And that uses a different element. Wow. That element is, what do you think? Mercury. We're going to use mercury. It is not something for the faint of heart. It is poisonous. You have to be careful. So we won't do that in lab, I'm sure. Unless Jay-Z has other things planned for y'all that I don't know about. Okay, so we're going to add water to an alkene. Okay, just like we've been doing. But it does not require acidic conditions. So what that means is there are no carbocations. Okay, so since there's no carbocations formed, you aren't going to get any rearrangements. Woohoo! Okay, so you got to remember. Yeah, you got to remember the mechanism a little bit. Okay, so this is a simple one, just a generic double bond. The way you add the mercury is you use a compound called mercury 2 diacetate. Remember that OAC? Remember what that means? Looks like that. Okay. And H2O and THF. Do you remember what THF is? It's been a while since you thought about that. Okay, here's THF. I'm going to have to draw it all in one swoop. I can't go back. It's off. Okay, so this is tetrahydrohydroTHF. Okay. THF is an ether. Okay, have you used ether in lab yet? Regular ether, which is ethyl O-ethyl. If you haven't, you've used it this probably. Okay, this is just another one that you can use. Okay, it happens to be one though that picks up water really easily. Okay, in this case, it's okay. You can have wet THF. That's what you want. Okay, and notice that there is a weird second step where you add that sodium borohydride, NaBH4. Okay. What ends up happening is you add water across the double bond. Markovnikov. So what does Markovnikov means? The one that has the most hydrogens gets the hydrogens. Okay, but no rearrangements. Okay. So here is how it works. I'm not going to ask you to redo this whole mechanism, but sometimes knowing the mechanism helps you remember the reaction. Is that true? No? Okay. All right. So look what happens in the first step. You have mercury adding across that double bond right there, and you make a 3-membered ring with mercury. Okay, a 3-membered ring with mercury. Then the water opens up that 3-membered ring, and it comes in from the back and opens it to the top. Okay, and then you have to deprotonate. But look what you still have on here. You still have that mercury on there. Okay, you get the mercury off by adding the sodium borohydride. Okay, that's what it's for, to get the mercury off of there. Okay? Are you with me so far? Okay, now, you'll notice in this step, the water has 2 choices. It could add to this carbon or it could add to that. But it adds to the one on the left. It picks that one. Have any idea why? Because this is plus. And so what happens is the plus charge gets shared with this carbon. And so it's kind of like a partial. So it pulls the water to it. Okay, so that's okay. Oh, and here's the little acetate thing. Okay, what would happen if an alcohol replaced water in the second step? So instead of having water, what if we had methanol, CH3OH? Methanol. What would we get? So we'll have the same compound. And we're going to add methanol. Wouldn't matter what alcohol, the same basic thing is going to happen. Okay, so where would this go? It's going to go to that same carbon, the more highly substituted one, because that's better at stabilizing a buildup of positive charge. Okay, so what are we going to end up with at the end? Instead of an OH, we're going to have an OCH3, just like we did in that other mechanism. Okay, same basic thing. Okay. Okay, now the reduction reaction, reduction is addition of hydrogen. The reduction reaction step, the mechanism is not fully understood, so don't worry about it. We'll just let it be not fully. Okay. They just know it works. Sometimes we just know stuff works, and we just accept it and move on. Okay, now look at the top one. What is the major organic product for the first one up there? What do you think you're going to get? So what do you do overall? We're adding what and what to the molecule? A what and a what? An H and an OH, okay? So where are they going to go? Bless you. Who gets what? I got clean. Who gets the H and who gets the OH? What do you think? Well, what are your choices? Is it just Friday, or are y'all just scared to death to say anything today? Is there a reason you're scared to death? Who gets the H and who gets the OH? And what happens to the double bond? It's out of here. Right. Okay, so who do you think is going to get the H? The one on the right?
Left.
The one on the left. Right, Markovnikov. Okay. So is that what you drew? No. Is that what you just said? Xander. All right, how about the bottom one? Who gets the H and who gets the OH? The one on the right gets the H, and the one on the left gets the OH. And notice that it does not rearrange. If you had done this reaction here, all right, what do you get? What would have happened? What would we have done? Would we have gotten that same product over there? No, because what would have happened? It would have rearranged. So what would we have got? Who's going to move? A methyl? A hydrogen? That's all I'm giving you. Okay, so the first thing that happens is this goes and grabs a H plus. So that H ends up here. I'm going to draw it on there like that. This would be a secondary carbocation. And then what would happen? This would move so that you get a tertiary carbocation. So it'll look like this. I'm going to squeeze this puppy over here. I don't know, maybe I should have restarted because I'm off. It's driving me nuts. Here, I'll draw the H on there, put the plus. Okay, and then what adds? Water. Okay, and then we deprotonate. Remember, OH minus does not add. Okay, water is in there. There isn't any OH minus in there, even though you get an OH minus on your mouth. Okay, so you would have gotten this one. So you can choose your conditions to get the one that you want, or the one requested in the problem, whichever way you want. Alright?
So I'm doing the mechanism that, say we do it on test.
For the mercury?
No, for
The bottom one, yeah, I skipped steps.
Yeah, because you're talking about how water adds. We have to show the H2O
Yes.
attaching.
Yes, if I want you to draw the mechanism out for this one. Wow. Okay. You would have to go in and do the rest of it.
And then show the H2O.
And then show the 8 getting pulled off. Yeah. Mm-hmm. Yeah, so don't forget the rest of it. Yeah, I'm trying to speed things up slightly. Ever so slightly. Okay, so what if you add water and sulfuric acid to the first one? What you gonna get? We're gonna get what? Who's gonna get what? One's gonna get an H, and one's gonna get no H. Do you not have it? Oh, really?
It's 4-5.
Oh, sorry. Okay, you can also do that with the mercury. Okay, so if you had Hg, OAC2, H2O, THF. Okay, and when you write these out, y'all, when there's a 1 and a 2, you got to have the numbers. Don't forget the 1, don't forget the 2. There's 1E and a 2E. Okay, and what was 2 for this? NaBH4. You got to remember that. Okay, either one of those, you would get that product. Okay, what if you wanted this one? Ooh, this one's totally different. What's different about it? How did it add? Anti-Markovnikov, right? Okay. So, well, you know, somebody wanted to make that one. Somebody wanted to do it. So, we got a way to do it. And it uses a whole nother element. It uses element B. What is B? Boron. What is bromine? Br. Br is bromine. B is boron. Okay, notice that we're using that THF again. Highly popular. Okay, and so you do BH3THF and look at step 2. No acid in here. OH minus H2O2 and H2O. What's H2O2? Peroxide. Yeah, hydrogen peroxide. Okay. All right, this is called Hydroboration-Oxidation. It's probably on the next slide. There it is. Okay, this is the hydroboration step. Okay, we're going to add borane to the alkene. It actually will happen 3 times, one after the other, and form what we refer to as a trialkyl borane. So you will have a boron, okay, that won't have any hydrogens on it. It'll have 3 of these on there. That's the trialkyl borane part. Okay? This is what diborane looks like. Boron is a weird element. If you find it on the periodic table, have you found it? Where is it? What number is it? 5. How many valence electrons does boron have? 3. So I'm going to go 1, 2, 3. So how many bonds can it make? 3, right? It's got 3 electrons to share. That makes sense. That's why it's BH3. Okay? Well, boron has a few issues. Okay, yeah, it's one of those elements. Because boron kind of wants to play with the big boys and have 8. And he's like, oh my gosh, I want to have 8. I want to have 8. But if he gets 8, he gets a negative charge. He wants to be neutral, so he kicks something off. And that's basically how it works. You're going to give boron too many electrons, and then it's going to kick them off, okay? Because it really can only handle 3 or 6 electrons, 3 bonds, okay? This is diborane, and you'll see it's written kind of weird, okay? Because it's trying to maybe get those 8 electrons. And so there are 2 hydrogens that are shared between 2 borons. We'll just write BH3, but sometimes you will see B2H6 written, and that's what they're referring to, is that. Okay, so let me write that up here so you see that. B2H6 for boron. Okay, now here is boron and THF, which is a real popular way to use it. It actually complexes with the O of the tetrahydrofuran. And notice you have a plus minus on that because the O has 3 bonds and the boron has an extra. Okay, sometimes that's written like this, BH3.THF. Okay, and here is our plain old BH3 with an empty p orbital, ready to react. Okay, so that's basically boring. When you do this first step, here, let me do this. I may have this on the next slide. I don't know, right? Okay, you're basically going to do this at once. It's going to add across the double bond, okay, and it's going to add at the same time. So one carbon's getting the B and one's getting the H at the same time. Okay, so that addition is going to be from the same side. What is that called? When the addition is from the same side. SYN. All right, let's see what I got on the next one. Okay, here's that picture I just drew. Okay, now this molecule that's up here is not symmetrical. Okay, boron has a high affinity for the least sterically hindered carbon, like super high. Like, I don't know I've even ever seen any where it went to the other one. Okay, so this is important. And here's the syn addition. Okay. Okay, now part of the reason is that in the transition state, all the breaking of the bonds and forming of the bonds is not equal, and the carbon that is more highly substituted will take on a little bit of a plus charge. Partial plus is all. I'm sure somebody's working on figuring out exactly what that percentage is, but I personally, I don't. I care, but you care less than I don't you? Okay, so there we go. So that's why we are adding Anti-Markovnikov. Okay, now all the fun stuff with boron happens in the second step. Okay, so when you take hydrogen peroxide, let me get, and you add base to it, okay, you're going to get an acid-base reaction. And that's going to give you that proton, and those electrons are going to go there, and you're going to end up with that OOH minus ion that you may have not seen in jar chemistry. I'd kind of be surprised. Don't mess with it. Okay, that's the ion that's formed, and that's what gets to do all the fun stuff. Okay, so it's going to go to the B. Why? Because the B only has 6 electrons. But oh my gosh, What happens then? The B becomes negative. And so one of those R groups on the B, remember we made a tri-alkyl borane in the first step. One of those alkyl groups, the B says, I'm kicking you off, okay? And it kicks it to the O, and the OH minus. Okay, and look what we have here, this OR. It's going to do that 3 more times, okay? Where the OOH minus from the hydrogen peroxide, that ion is going to add to the B. The B is going to go, oh my gosh, I'm negative. I don't want to be negative. And it kicks an alkyl group off. Poor boron. It has a difficult life. Okay, has a lot of issues. This has issues. Okay, so here's where we ended up. Okay, and then you're going to have OH, all these OH minuses now are going to add to the boron and kick out the alkoxide ions, which then get protonated. Okay, and it does that 3 times. Okay, we add, 1 leaves, we add, 1 leaves. Okay, so look what you end up with that boron, this little deal. And you get 3 alcohols. Okay, enough? I mean, yeah, it's kind of weird because it's different, but it's all because of the chemistry of boron. Okay, there was a guy named H.C. Brown who came up with a whole ton of stuff that you could do with boron. This is just one. Okay, like his whole career was done with boron. Oh, and I forgot to tell you, the exciting part about diborane is that it's flammable in oxygen. So if you were to pour it out of the bottle or open the bottle, it would light on fire. Okay? So the way you have to work with it is you have to use syringes, argon atmosphere, and you have to like you push in extra argon and then you pull out what you're taking out so it doesn't end up under reduced pressure in your bottle. And the bottles have things on them called septums that allow you to put needles in and out and not mess them up. Okay. And so if you took a syringe of diborane out and pushed the plunger.
How long would it?
It's pretty quick, I think. But you don't want to set anything else on fire, you know. Okay, so it's something that you have to be really careful with. I have not gotten to work with diborane. I'll live my life without getting that. I worked with other things that were could burn up, but not diborane.
What did you work with? Okay.
Oh, when I caught the sink on fire, that was that was basically sodium and acetone. I mean, it was like, it was a simple little thing. It was, I told you all that story, right? No, Karen, let's go to another place you're in. All right, so when you work with THF, let me draw the little picture of THF for you. Okay, I was working with THF and I needed it to be dry, not wet. And it picks up moisture really readily, okay? So what you do is you put sodium metal in there, like you make, it's called sodium shot, where it's just little balls of sodium. And you put those little balls of sodium in there, and it'll react with the OH, the water, to make sodium hydroxide, okay? When all the water is gone, you have something in here called benzophenone. It's benzene, carbonyl benzene. Okay? When all the water has been reacted with the sodium gives an electron to this, and it turns blue. So the whole THF thing, we call it a still, the whole thing will be bright blue color. Okay? It's really pretty, actually, like your shirt blue, seeing your shirt. Okay, so then what you do when it's all blue, and you have this under a nitrogen atmosphere, dry nitrogen, you then distill over how much you need. So if I need 10 mils, I've got this whole thing, I only distill over about 10 mils, measured out and use it. Okay, you don't have to be so hyper about the THF that it can't be in the atmosphere, but if you left it out overnight, it'd pick up moisture and you'd have to start. Okay, So that was the deal, okay? I had a THF that I had used for a while, and so you have a little thing that you go through, a little procedure to clean it up at the end. So I was cleaning it up. So you go down the line, you put methanol in, and then that reacts with the extra sodium in case there's any in there, and then you put ethanol in there, and it does that too. Okay, and then you put water in there, and it had done all the stuff it was supposed to do. All the bubbling was gone. Well, then all you have left with are all those salts, so you just wash them out. So I was washing it still. And we have these big sinks, like this big, this deep, that you do your dishes in the lavatory. So I'm doing the dishes, and it was after hours. And me and my buddy Lynn were there. It was like 7 o'clock at night. And I'm doing my dishes, because that's what you do in your time. And then I said, oh, Lynn, look, there was a little piece of sodium still in the THF that had not gone through getting killed by all that other stuff. I said, come here, look, it's really cute. And so we're over there looking over the sink, and the water's running, and the little sodium is going. The next thing we knew, the whole thing went whoosh and lit on fire. Like the whole thing, because we had been using acetone to do dishes. And so the acetone is really what lit on fire. And Lynn and I went, oh, and stepped back. And remember, the water was running. We watched the flame go down. And there was the pipes they use a lot of glass pipes in chemistry labs because they're much more impervious to chemicals. So you could watch the pipes go down. So then, lab smells, we could smell it and everything. And we're like, oh my gosh, because the boss was coming. He said he'd be here. Oh my gosh. So we're trying to get all the smoke smell and everything out of there. So we're running the water more and more. It was kind of fun. We wondered if there was anyone on. We were on the third. If there's anyone on any of the other floors looking at their pipes and going. But we never heard that. So I think we would have heard. It was pretty funny. It's pretty funny, yeah. Yeah, I'll have to ask my buddy Lynn if she remembers that. Because I was the one who really did it, you know. She didn't really do it. It was she just was my buddy. Keeping me safe, that's what she was doing. All right, so what are you going to get from this one? I didn't tell you all this, right? You usually tell it first semester. Okay, so what do you get from this one? Okay, now it says 1 and 2. First of all, you don't have to show me the product after step 1. Okay, you can just draw the product after step 2. But sometimes drawing the product after step 1 helps you figure out the product after step 2. Okay, but it's not going to be required. If this was a problem on the test and you had to draw the structure of the major organic product, okay, it would be like that. Okay, you would only have to show the product at the end. Okie dokie. If that helps you at all. Okay, so what is the overall process? What are we doing to the double bond? We're adding a H and an OH, okay, across the double bond. Who gets the H and who gets the OH? The one on the right gets the it's Anti-Markovnikov. Boron is Anti-Markovnikov, AB. Anti-Markovnikov boron, AB. That help?
So is it because boron or because of the peroxide?
It's because of the boron. The peroxide ends up getting you the OH. But the boron is the okay, after the first step, this is what you would have. And you would have 3 of those on there. Okay, so see the H is on there now. In the first step, you put that H on. You don't get the OH on until the hydrogen peroxide. Oh, Okay. Okay. Now, how about the next one? What do you think we're going to get? Are y'all hot? I'm hot. And I don't think it's a hot flash. All right, I'm going to open another. All right, now you can open this one. Be more confident about I have to tell my coach it's for Okay. Okay, so what are we going to get on this one? What do you think? Does it rearrange? That's a good question. That's a question that you should think about. Does it rearrange? What reactions rearrange? Ones that form, was any carbocation formed at this mechanism? So is it going to rearrange? Okay. All right, that help? Okay, so you got it? You ready for me to push a button? Is that what you put? You didn't even do it. Okay, so this carbon is going to get the OH, and this carbon is going to get the H, and there's no rearrangements. Oh, and on a final note, when the boss came in later, he didn't. Yeah. What do I have? Why do I have that? Oh, we're going to add X2. That's why I have this. Okay, we're going to add X2. So what do you think this is called? Yep. Oh, can't write. Is it on your slide?
Yeah, underneath that.
Oh, I didn't see that. Psi. Okay, there it is. There's just on there twice. Okay, so we're going to add X2. Okay, I2 is too endothermic to be useful, and the products are unstable at room temperature. So I2's out. F2 is too hard to control. It blows up. No, I haven't done that one. Okay, so the ones that get used are going to be chlorine and bromine. Okay, for solvent, we use small chlorinated ones like carbon tetrachloride, chloroform, methylene chloride. Have you used some of those in lab? Okay, they are nice solvents that typically are very nicely unreactive. Okay, so here's our double bond, generic one. Okay, we're going to add X2, X being chlorine or bromine. Okay, and what are we going to get? One carbon gets up, and the other one gets up. Yeah, yeah. XX. Okay, that is called a vicinal dihalide. What does vicinal mean? Carbons are next to each other. Carbons are next. Okay. Do you think it's going to be Markovnikov or anti-Markovnikov? Neither. Is there an H involved? No. Okay, so for Markovnikov and anti-Markovnikov, you have to have H something. Okay, H something. There's no H something. Okay, it's two X's, so one gets one gets the other. Okay, so what do you think we get from the first one? Yep, we're going to add a Br to each of the carbons of the double bond. Okay, here we go. Is that what you got? Yeah, count your carbons, make sure you do it right. Let's not make silly mistakes. Later on, you cry at me. I made such dumb mistakes all the time. Okay, count your carbon. Nothing wrong with counting your carbons. Now, you need to recognize that this is the solvent. Okay, so the solvent is not doing anything except providing a media for the reaction. It is not getting involved in the reaction. Okay, same thing down here with methylene chloride. Okay, so what do we get from the one on the bottom? One gets a, and the other one gets a chlorine. Okay, all right, so I want to do this mechanism. You'll love it. Okay, what about this one? What am I going to get? One carbon's going to get a, and the other carbon's going to get a. So what does that look like? I'm going to draw this up here. Dibromocyclopentane. Okay, how many dibromocyclopentanes are there? 1, 2 dibromocyclopentanes. There are 2, right? One is cis and one is trans. Oh my gosh, I'm telling you, it all comes back. All right, so which one do you think it's going to be? Well, that ain't going to tell us. It's this one. They got an 80% yield, and it was the only product. Okay. Let's see what else I put up here. Oh, that's right. Okay. The addition of the 2 bromines is anti. Have you used bromine ever? Only in General Chem did you do a lab with bromine? Do you remember anything about it? It's real dark red color and it's heavy. Heavy and red. Heavy and dark red. Kind of maroonish more. Okay? This reaction occurs like that. Okay? So if you have a test tube that has a compound in it and you add dark red Br2, bromine, to it, okay? What happens is, as it adds, the color dissipates because it reacts that fast. And so you get the trans one, and this has been used as a test for double. Okay, because the solution goes colorless. We call it a test for unsaturation. Do you remember what unsaturated means? You have a double or triple bond, okay, between carbons. Not like carbonyls, that's different. Okay, since trans is the only product, no cis, that tells us that there's no carbocation organism. Is there going to be any rearrangements? No. Does that make you happy? Yay, on Friday I made you happy. Okay. Wait? Yeah. Well, wait. Oh, now look what you made me do. I have to push all my buttons again. What is the problem? You didn't write that down?
There's a lot to write.
Oh, there is. Okay, so. Did everybody get all their lot to write? Okay. All right, I got 2 minutes to do the mechanism. Okay. Well, it's about 2 steps, so. All right, so what's going to happen is this is going to react with the bromine, and an electron pair from the bromine is going to go down there, and this is going to leave. That forms something that looks like this. A 3-membered ring with a bromine in it. The bromine, something that you probably haven't seen, has a plus charge. Why does bromine and chlorine do this? Because they're pretty large. They can hang out with that. This has a special name. It's called a bromonium. Okay, what happened to the Br at the top? What did we get? Br that you're more used to, Br minus bromide, okay? So what's going to happen now, we got our 3-membered ring. It's like having a built-in leaving group. Our bromide is going to come in from the bottom and open that up to the top. So it's like a backside attack, but the leaving group doesn't leave. Okay? So you end up getting your bromines on opposite sides. That's it. That's the mechanism. Chlorine is exactly the same, except you have chloride and chloronium ion. Chloride and a chloronium ion. Okay, not too bad, huh? And you even got one of my stories out of me. Y'all see, look, I got a picture of the bromonium ion for you. All right, so I'll start with that next time. I don't know I'm going to say much about it, but I'll start with it.